Hello students, welcome to the class of Digital Communication System. Today we are going to discuss on the topic of pulse analog modulation. We have already covered the types of sampling and the sampling process. We also did the mathematical representation in our previous lecture. So today we will be covering this pulse analog modulation. It is similar like the modulation we studied in analog communication, but here the carrier signal is a train of pulses rather than a sinusoidal wave. That's the major difference. Here you are going to study three different types of pulse analog modulation. That is the pulse amplitude modulation, pulse width modulation, and pulse position modulation. How we modulate the signals using these three techniques and how we demodulate. These are the major things that we are going to study in today's class. After that, we will move on to the pulse, discrete pulse modulation or the pulse digital modulation of that will cover the PCM, pulse code modulation. So let's talk about the pulse analog modulation. That is the first one here is the pulse amplitude modulation. First, let's talk about that. So pulse amplitude modulation is the type of modulation in which the amplitude of the regularly spaced rectangular pulse vary according to the instantaneous value of the message signals. Pulses may be either flat top or natural samples. See, when we studied the modulation scheme earlier in case of analog communication, we saw that we are varying certain parameters of the carrier signal. In case of amplitude modulation, amplitude of the carrier was varied according to the message signal. In case of frequency modulation, frequency of the carrier was varied according to instantaneous value of the message signal. And in case of phase modulation, the phase was getting varied. Though the amplitude, frequency, and phase of the carrier signal was varied according to the instantaneous amplitude of the message signal. Fine. Here what we are going to do, the carrier signal is our rectangular pulse instead of the sinusoidal pulse. So rectangular pulse amplitude is going to vary according to the instantaneous value of the message signal. This is the sample and hold circuit. The same funda that we studied regarding the flat top samples is going to be studied here. You can create either flat top samples or natural samples, but right now here I'm going to discuss the creation of the flat top samples. You have already studied about how to create the natural samples. Instead of using this discharge tube and discharge switch, you can just take the sampling switch and the capacitor. You will create the flat top samplings by varying the amplitude of the signal according to the message signal. But here what we are doing is, if we take this instant, we are going to keep this instant fixed for this full tau duration. This is the major difference between the flat top samples and the natural samples we have seen in our previous lecture. So now what we are going to do is, this is a sampling switch, this is a discharge switch. We can take MOSFET or BJT. MOSFET is a better switch, so we will take that. Here in the gate of the MOSFET, when we apply the pulse, that time the capacitor starts to charge to the instantaneous value. After that, we remove this sampling switch, means we put it off and the discharge switch is put on, and the capacitor is going to discharge to zero with the help of this discharge switch. So for that duration till it discharges, the same instantaneous value is kept. And in this way, we are creating the flat top samples. So here it's given, the writing is given for the process. The sampling switch is closed for a short duration by a short pulse applied to the gate of the transistor. Obviously, we know from the MOSFET theory that the gate is acting like the input part. Is the gate. When you give the gate voltage more than the threshold voltage, at that time the MOSFET turns on. So that is the thing. So we are applying a short pulse to the gate of the transistor G1, and during this period, the capacitor is charged to the instantaneous sample value of the message signal. When the sampling switch is opened, that means when it is switched off, the capacitor is holding that charge and it is discharging through the discharge transistor, or you can say the discharge switch. So it will discharge to zero, and again the same process is going to be repeated. So these are the waveforms, spam waveforms. You can see the same waveforms are there. That was for the that we studied for the flat top samples. This is your message signal. This is the direct delta function or the train of impulses, and this one is the rectangular function. So ST and HT, when you multiply, when you convolve these two, then you are going to get HT only. So finally, GT is equal to ST into convolution of HT. So this way you are going to get the PAM waveform. So this one was the circuit description and the other one was your mathematical description for the modulation of the PAM signal. So if you want to go through this process, let us see once more process when we are doing it with the help of the mathematical process. Let's see for once. So what we are going to do is we have this signal delta SXT was our main signal. Then we had the signal delta TST. So the delta TST was our train of impulses. We are going to multiply this with the HT. So this one was actually delta of T minus NTS. And this one was of HT minus tau, that is the width of the pulses was tau. So finally what you are going to get is HT minus tau, and this is also going to be multiplied when you are this one is actually ST. This one was your ST. XT is first multiplied with ST. ST was your sampling signal, that is the impulse one. Then this ST was multiplied with HT. So XT is your message signal. After that you had this ST, which is delta TST into HT. And then finally you are having this GT, that is XT into ST. XT into ST. So the sampling signal is the same, that is your rectangular pulses. In both the cases, it is the train of rectangular pulses only, the sampling signal. In both cases means in the case of flat top samples and the natural samples, but the flat top sampling method over here is used. So XT into ST will give you the sampled signal. Finally, the expression for this sampled signal in the time domain, you can write it as X of NTS and H T minus NTS. Fine. From n is equals to minus infinity to infinity. This is GT. So here this part will be this part will be NTS. H of T minus NTS. When delta T minus NTS is multiplied with this one. Fine. Okay, now let's move to this how to demodulate it. So for demodulating the PAM signal means that you have been given the PAM signal and you want the demodulated signal. That means you want the original signal XT. So the PAM signal is given in the holding circuit where it is consisting just of a switch and a capacitor. It is going to hold the sampling value and then reconstruct it. That is it. And before reconstructing, you are using a low pass filter to just remove the high frequency component. It's very easy. So what you are going is to do is taking this value at that instant and holding it for the time constant. That will make the reconstruction possible. So what are the advantage and disadvantage? See, since PAM signal is varying the amplitude of the sample, so amplitude contains the noise. That means the noise is affecting the signal, the modulated signal. So PAM is susceptible to amplitude changes which can reduce signal quality and causes information loss. On the other hand, the large bandwidth is also required. The goodnesses of PAM is that there are simple signal processing methods like filtering and demodulation are made possible by PAM. Okay, now we are moving to this PWM, that is the pulse width modulation or the pulse duration modulation or pulse time modulation. So in this case, what is going to happen is the amplitude is not varied for the carrier signal, whereas its width is going to vary. So the width of the message signal will change according to the, width of the carrier signal will change according to the instantaneous value of the message signal. You can vary three types. The width you can vary in three types. Either you will keep the leading edge constant and trailing varies according to the message signal, or trailing is kept constant and leading is varied, or both trailing and leading are varied. So both the trailing and the leading are kept constant and the center varies. So let us see what is meant by this trailing and leading edges. So first let us do this part of here. Over here, let's do it. What happens? Okay, so this is your message signal. First, I will draw a sawtooth waveform. So this is your sawtooth waveform. There was a sawtooth generator. Okay, you can see over here, this one I have drawn as a sawtooth waveform. And above this, I will put a message signal. See, I'm taking the message signal in this manner. Now, if I want the pulse amplitude varied signal, how will I get it? Let us see. We will take all the trailing edges. So this one is the leading edge of the sawtooth. This is the trailing. Trailing means the ending one. So these are the trailing edges. We will take the trailing edges of this. Fine. So let us move it for some more time. Okay. So I will take this part also. Fine. So now you can see this is the trailing edge, where it means the portion which is going down. This one is the leading. Now at this portion you see the sawtooth waveform is down and the message is up. So the comparator output will be high. So you will get a high signal over here. But it's a 1 over here. Till what duration? Till the duration of this. This is your width. Now it will become low again. Again, you see over here the message is high. So till this point, it is going to be high. Again, now you can see the sawtooth is high. So here it is going to be low at this point. Now what I am telling is, just let me show you in the slides. See, here you have a op-amp as a comparator. So the modulating signal is applied at the non-inverting terminal and the sawtooth generator signal is applied at the inverting terminal. What the work of the comparator is, it will compare the modulating signal with the sawtooth generated signal, and if the modulating signal is more, then it will give a positive output, means it will give a +1 and high output, and if the sawtooth generator is higher, then it will give a lower output, means the output will be 0, or you can say a low output. For the timing, just ignore this monostable multivibrator in the circuit. Just take the circuit as a op-amp as a comparator is given. In the inverting terminal, you are applying the sawtooth generator. In the non-inverting terminal, you are applying the message signal, original message signal or the modulating signal, and at the output, you are getting the PWM signal. So the function of the sawtooth generator here is to produce the ramp signal used as sampling signal. So sawtooth generator is producing the ramp signal, which is used as the sampling signal, and it is applied at the inverting terminal. Now message signal is applied to the non-inverting terminal. Now the principle of working is that the comparator output will remain high as long as the message signal amplitude is higher than the sampling signal. Means at those points where the message signal is higher than the modulating than the sawtooth generated signal, that time the comparator is going to give you a high output. Now see over here. As the amplitude of the message signal increases, the width of the pulse increases. So this is another very important point, which is the principle of PWM over here. As the amplitude of the message signal is increasing, see here the amplitude is more than this point. Here the amplitude is decreasing, so the width is lesser. Here the width is more than this one. In this case, the width is more, much more, right? How you have drawn this width, just see this portion is called the trailing edge, this straight one line. This one is the trailing part. This is the trailing part. So keep the leading edge of the PWM signal coincides with the falling edge of the ramp. So leading edge of the PWM signal. So we are starting at this point, leading edge of the PWM signal is this point, trailing edge is this one. The leading edge is coinciding with the falling edge. So this is falling edge of the what? Falling edge of the sawtooth generator. So this is for the synchronization purpose. You have to understand that when this is falling, that time this is the leading edge of the PWM signal. Now from here, if you take till the point it is intersecting, that time the sawtooth generated wave. This one is a sawtooth generated wave. This is lower and the message is higher. So the output is 1. In this portion, you see sawtooth is above and message is below. So the output is 0. In this part, again the message is above the sawtooth generated signal. So it is 1. So there are 3 things that you have to keep in mind. First thing is that as the amplitude is increasing, the width of the signal is, width of the pulse, width modulated signal is increasing. Here you can see the amplitude is decreasing. So the width is decreased. Here you can see as the amplitude is increasing, the width is increasing. So we are keeping the leading edge of this pulse width modulated signal fixed and we are varying the trailing edge. Actually, the trailing edge is varying according to the message signal instantaneous amplitude of the message signal. This is the principle of PWM over here. Once again, I am explaining. You are taking a op-amp as a comparator, applying the sawtooth generated signal, or you can say the ramp signal in the inverting terminal and message signal in the non-inverting terminal. What we are going to do is comparing which one is higher. Whenever the message signal is higher, output high will go. Whenever the sawtooth generated signal is higher, that time 0 will be the output. Now, how to generate the PWM? What is the criteria? How you are generating? One edge of the PWM signal, that is the leading edge, is kept fixed. And how it is kept fixed? It is made synchronized with the falling edge of the ramp. So this one has been kept fixed, and then you are seeing the width by the intersection point. So where next time wherever it meets, till where it is higher, you can say till the point the message signal is higher, that much is the width. Another important thing that you have to keep in mind is the principle that says amplitude, as the amplitude of the message signal is increasing, the width of the pulse is increasing. Now for demodulation of PWM signal, demodulation means what? You are giving in the input PWM signal. So PWM signal is given in the input, and finally at the output you will get the continuous waveform. So what we can do is we will apply the PWM signal, which is obviously containing the noise. So that is applied to a pulse generator or a Smith trigger. The Smith trigger will generate a clean PWM signal, means it is going to remove some of the noise. After that, the output is going to the ramp and pedestal generator and a reference pulse generator. So this is very, very important, a reference pulse generator, which is going to be help in the synchronization of the edges of the pulses, and also that will be the synchronizing has to be done for the receiver and the transmitter. So this reference pulse generator will be a fixed width and fixed amplitude signal, and that the pedestal generator will be and the value means the output from the pedestal generator and the reference pulse generator both will be added, given to a clipper and a low pass filter, and finally you will get the detected output. Let us see how this is going to happen. First, let us see this part. This is your PWM plus noise. Now the top of the thing, you can see it is having some harmonics, so those are the noise, so it is getting removed. So regenerated PWM. After this, you see over here, from this point till the width of the pulse, there is a ramp, right? And then that value is held constant. Again, when our next pulse is coming, next PWM pulse is coming, that time it goes down and starts to create a ramp. And finally, it creates the ramp for the full duration of this, and then it holds the value. After this, this is the reference pulse generator. This reference pulse generator is synchronized with the leading edge of the PWM pulses. So let us see over here what is happening. Ramp and pedestal generator, constant slope ramp signal are generated as the output of ramp generator. Max ramp voltage is retained till the next pulse. So the maximum ramp voltage is retained till the next pulse. Generates constant amplitude, constant width pulses synchronized to the PWM pulse, leading or trailing edge. however delayed by a fixed amount. So this is very important. See, these signals will be synchronized either to the leading edge or the trailing edge of the PWM. Here also it could be there, but there is a fixed amount of delay. So we have taken this much delay, and then at the leading edge of this we applied a signal over here. Same way here we are applying the next signal. You can apply it at this point also, but after that you will have to keep the delay as constant. But all the delay, the amplitude, width, all has to be kept constant because this is a reference bus generator. Then you will add these two. There was an adder, right? So this ramp signal plus the the reference signal, both you are adding. Finally, you are using a clipper and clipping it to generate the PAM pulses, so that you are getting in the output as the PAM pulses. And after that, you don't know how to demodulate the PAM. You will use a holding circuit and a low pass filter. You will get the original message signal. So from first you will generate the PWM. First you will generate the PAM from the PWM, and then you will get the original message signal in the form of the original, or means you will get the original message signal. Let us see how we are going to do it in the this portion. So here you have generated the message. Now what we are going to do is, suppose this one is your pulse width modulated signal. Okay. Now you are applying a reference pulse generator also. So at this point, you can see over here that it has been made. You'll have to draw these lines over here properly. Now till this point, it is going to show the ramp. And then finally, it is going to hold the maximum value of this ramp. Same way, when the next pulse is coming, it is going down. Again, it will charge up, hold the maximum value of the ramp. Again, it will hold it till the next pulse comes. Till this point, it is going to hold it. Fine, it is not being seen at, then again this point it is going down. Again, now again it is going to, it is depending upon the width of this one. So the width will be equal to the slope of the ramp. This is the way. It's not being seen clearly over here. But in some cases, if the width is more, the ramp is more. If the width is less, the ramp will be less. So see over here. At this point, the width is more. At this point, the width is even more. So the ramp is going to the highest value. This way, the ramp has been created, and this is a constant pulse generator, reference pulse generator, which will create pulses of fixed amplitude and fixed width. Finally, you are adding these two, and then you are clipping. Clipping, however, will take the clipper level, that is decided by you, and then you can get the PM pulses. From the PM pulses, you can then demodulate and get the original message signal. So there is less effect of noise. This is a very important advantage of the PWM signal, that there is a less effect of noise, as the noise is contained in amplitude variations, and we are not varying the amplitude, we are varying the pulse width. So, but here the problem arises that you have to design it in such a way that it is able to handle the maximum width. Although the average power transmitted can be low, but you have to handle the maximum width. And in order to avoid any waveform distortion, the bandwidth required for PWM communication is large as compared to the bandwidth of PAM. Now, finally, we are coming to the PPM, that is the pulse position modulation, is an analog modulation technique in which the position of each pulse varies with reference to the position of the reference pulse varies according to the instantaneous sampled value of the message signal. Synchronizing pulses are sent to keep the transmitter and receiver in synchronization. So see, over in the previous one, we have already generated a PWM signal. You have understood how we are generating the PWM signal. Sawtooth generator, and the input signal is given to the comparator. Now, what is happening to generate the PPM? You will use a monostable multivibrator. Now, what is the function of the monostable multivibrator? It is having one stable state. The low state is taken as a stable state, and whenever a trigger pulse is given, the output will become high. for a certain time period decided by the RC components of the circuit. So what is going to happen is that the PWM signal is going to act as the trigger for the monostable multivibrator. It is normally going to remain low. Whenever the PWM signal will come, it will become high. And this way it will generate PWM pulses, PPM pulses. Let us see. This was the PWM output, the comparator output. Now, whenever the PWM signal is coming, it can be the leading edge, it can be the trailing edge. So here we are taking the trailing edge. So at this point, when the pulse is there, the monostable multivibrator, the output goes high and again it becomes low. This duration is decided by the RC component, and see, this duration is fixed. The width of the pulses are fixed. Fine. But the position will change. See, again the PWM output is going high at this point. So you can see over here that this is again the same, but whenever this is PWM output is coming, that time a trigger is generated and the monostable multivibrator, the output becomes high. The PWM pulses obtained at the comparator output are applied to a monostable multivibrator. The monostable is negative edge triggered. Hence, corresponding to each trailing edge of the PWM, the monostable output goes high. It remains high for a fixed time decided by its own RC components. Thus, as the trailing edge of the PWM signal keeps shifting in proportion with the modulating signal, the PPM also keeps shifting. Fine. So when message signal goes high, distance between the pulse increases. When message signal goes low, distance between the pulse decreases. This is the principle of the PPM. So over here you can see that when the message signal is going low, this is the message signal is going high. That time the distance between the pulses is increasing. It is going even higher. The distance between the pulses are increasing more. Now the message signal is decreasing, so pulses, the distance between these two pulses are decreasing. So this is the principle of PPM. So if what you how you will write the principle of the PPM is that when the message signal is rising or getting going higher, that time the position, there is more difference between two PPM signals, or the position is having the width. You cannot say the width. The position, the two pulses are varied by a larger distance. When the message signal is going down, that time the distance between the two pulses is decreasing. Now the demodulation of PPM. For the demodulation of PPM, again we are taking a pulse generator and a reference pulse generator, and we are applying these two to the RS flip-flop. So you know the functioning of the RS flip-flop, that when the, here what is happening is when the R is the reset and S is the set. So flip-flop is on when the reference pulse is arriving, and it is set off by the PPM pulses applied at the reset terminal. So the PPM pulses which is applied at the reset terminal which set it off, and the reference pulse generator will make it on, and then that time you will get the PWM output. Finally, as the amplitude and width are constant, the power handled is also constant, and the synchronization between transmitter and the receiver is a must. This is the major work done by the PWM. So here what is the advantage and disadvantage? As the amplitude and the width are constant, so the power handled is also constant, and there is the synchronization is required between the transmitter and the receiver. That is a major thing that you have to look for. Fine. And this part, how it is going to happen, that whenever a reset pulse is arising, let us see over here. Give me a second. So what is going to happen is there is a pulse applied at the, okay, there is a pulse that is the monostable. See, one side was the output of the PPM pulses. So one side you will have the PPM pulses. Over here, let us draw it. So this is your PPM pulses, say. These are your PPM pulses. Now there will be a reference pulse generator which will be at fixed points. So say it is at this point, then this point, then this point. Now these are at the fixed intervals. Fine. So what is going to happen is, whenever this one is at the reset pin, this is the ppm pulse, this is the reset, and this one is the set. So the output will be this way. Whenever the reset is coming, it is going to be 0. So wait a minute, I'll just redraw it. So here you have the ppm pulses. And here I am drawing the reference pulses. This will be coming at a fixed duration. Here you have to take, though both the pulses cannot come at the same time. So you have to use certain restrictions in the design. So let me just remove this pulse from this point. And you are keeping it in between over here. Because see, if R and S both are high, that time there is no stable state of the flip-flop for the RS flip-flop. So that's why we cannot keep it. Now here see, when this is the set pin and this is the reset. So when this is there, then it is high. Once this one is coming, that time it will go low. Again, when this is coming, then it will become high. And it is going to remain high till this one is coming, reset one. Fine. It will remain high till this reset one is coming. Finally, again, this is going low and here one pulse has come. So it will come high at this point. Again, that reset one is coming at this point. So at this point, it is going to become low. So this way you are going to generate the modulated PWM signal. And after that, the PWM signal, you know how to demodulate. So after that again, the same process of PWM demodulation, that you will use this portion. This portion will be there. Yeah, this part. Ramp and pedestal generator, this will be the PWM signal. Now ramp and pedestal generator and given to the clipper, then low pass filter, and finally you get the PAM. And then from the PAM, again you will have those holding circuit and the capacitor. So this is all about the PAM, PWM and PPM. Just I will do final revision once again in a very short form. So for the pulse amplitude signal, you are using this circuit, which is a sample and hold circuit, where there are two MOSFETs and one capacitor. Both the MOSFETs are acting like a switch. The sampling switch is charging the capacitor to the instantaneous value of the message signal, and then it is switched off. This capacitor is going to hold that charge and it is going to discharge simultaneously through the discharge switch. So this way we are generating the flat top samples. And the mathematical description, I said, here you are using the rectangular pulses of width tau, or any width you can say, and the time period is Ts. That was it. So this is the flat top samples or the PAM signals. And when you are demodulating it, you will use a holding circuit. The holding circuit will consist of switch and capacitor, and then again a low pass filter to reconstruct it. The disadvantage is that since it is varying the amplitude, the noise is introduced, and the noise is creating issues over here, which is leading to the signal loss in the signal quality. Next we came to the PWM. PWM signal, for the generation of the PWM signal, you are using a op-amp as a comparator. And the working is that the comparator output will remain high as long as the modulating signal or the message signal is higher than the sampling signal. So here I explained you the process. The principle is that as the amplitude of the message signal is increasing, the width of the pulse is increasing. And how we are drawing these pulses, we are keeping one of the edge, we are holding one of the edge. Say here we are taking the trailing edge of the sawtooth generator, and then the leading edge, and then this one, the trailing edge of the sawtooth generator, and this is the leading edge of the PWM. So leading edge of the PWM is kept constant, and the other one is varied according to the width, or you can say according to the value of the message signal. Till the point the message signal is higher, it will be high. Then when the message signal becomes lower than the sawtooth signal, it becomes slow. After that, the PAM demodulation. For the demodulation, the PWM demodulation, we were taking first passing the signal PWM signal through a Smith trigger, which will remove the noise. That will generate a clear, you can say, a regenerated PWM or a better PWM. Then there is a ramp generator. So what happens is how the ramp is generated. This is important. Constant slope ramp signals are generated as the output of the ramp generator. Max ramp voltage is retained till the next pulse. So the slope is remaining constant throughout, but the value is going on increasing, and it is the width according to the width of the PWM signal. At this width, then it is retained. The maximum width, that amplitude is taken and it is retained till the next pulse is coming. So this way the different ramp signals are generated. Now this ramp signal is added with the reference pulse generator, and you get an output like the one shown over here in E. And then you're using a clipper according to the level you want. Mostly we are not taking these levels. We want the PWM signals. So we are taking these words. Now these are already generated pulses. Now we can see over here the amplitude of the pulse is different. So this is a PAM signal. After that, you can again use the PAM demodulation, holding circuit and low pass filter. So the advantage and disadvantage, less effect of noise, but the power that you have to use is more, because the different widths pulses will have different power. In case of pulse position modulation, the synchronization is very, very important. So for generating this, you will generate first PWM, that by using that comparator, and then after that you will give it to a monostable multivibrator. The trigger for the monostable multivibrator is your PWM, and then whenever the PWM signal comes, that time the monostable multivibrator comes in the on stage or in the high stage. Otherwise, it remains in the stable low state. So this way, and the principle goes that whenever message signal goes high, distance between the pulse increases, and when message signal goes low, distance between the pulses is decreasing. So this is the waveform you can see over here. Now this is the PPM output. The trailing edge of the PWM signal is kept as for the reference over here. So at the trailing edge, you can see the PPM pulses. When the trailing edge is coming, that time the trigger is there for the monostable multivibrator, and the output of the monostable multivibrator goes high. Over here, you can see as the amplitude is increasing, this one and this one, you can understand that as the amplitude is increasing, the distance between the pulses are increasing. Here amplitude is decreasing, distance between the pulses decreasing. Now demodulation of PPM, you are using a RS flip-flop. The R is the reset and S is the set pin. In the reset pin, you will be giving the PPM signal, and in the set pin, you will give the pulse generated signal. So what is going to happen is that whenever the pulse PWM signal is there, the flip-flop is on when the reference pulse arrives, and it is set off by the PPM pulse. And this way you will generate different PWM signals. We already saw this. As the amplitude and width are constant, the power handled is also constant, and the synchronization between transmitter and receiver is a very, very must thing for a PPM signal. So this is all about the pulse analog modulation. And with this, we have completed sampling and pulse analog modulation. Thank you, everyone. In our next class, we will be doing pulse code modulation. Let's meet in the next class.